The following program is brought to you in living color. The whole Earth will be brought to you in living color, visible and invisible. Your children's children will tell it, how in the 20th century people went into space, saw the whole Earth, and learned that we live on a rare and precious world. Space journeys have shown us other planets, barren and wasted, in startling contrast to our one and only Earth. Yet we face many problems, such as giving the world's people enough food to eat and enough clean air to breathe. We are starting to control visible pollution, but most pollution is invisible. How can we see all the kinds of pollution? We are increasing the yield of our farms. Still, we lose up to 1/5 of our crops every year through blight and disease, mostly invisible until it's too late. How can we see the sick crops in time? How can we see, looking down on the Earth, the many invisible things which need to be seen? We can see them if we learn to sense not only the light which made these photographs, but also the hidden radiation constantly coming from the Earth, such as infrared and ultraviolet light. The light you see is recognized in terms of colors. And now, even that light you cannot see can be recognized in terms of other colors. Colors I call invisible colors. How can we use them to fight blight and disease, to fight pollution, to help understand and manage Earth resources? A new technology called multispectral sensing reveals invisible light in new ways. In these visible displays, colors can be assigned arbitrarily. For example, red is often used for infrared. In this film, you will see how our vision can be expanded. You will see how these technologies show us the whole Earth, and you'll see what kinds of problems can be solved. To start, let's take a closer look at color. Here is a familiar object giving off more light than you can see, infrared light, which you can feel as heat. In the electromagnetic spectrum, visible light is limited to a narrow band less than 1 octave wide. You see red light about 700 nanometers in wavelength. Other colors extend to violet, about 400 nanometers in wavelength. You see less than 1 octave of light. How would it be if you could hear only 1 octave of sound? A player piano puts out a wide range of sound frequencies. People hear over a range of 8 octaves. A young person of high school age hears even more. Suppose you could hear only about 1 octave. Let's block off the notes, all except about 1 octave. Your eyes are limited to a 1 octave band of vision. And just as 1 octave is not enough to hear the full range of the player piano, so 1 octave is not enough to see what you need to see for Earth resources. The 1 octave you see is a small part of the whole light spectrum. Here, on a scale corresponding to the piano, are the extra octaves of invisible color. Beyond violet, ultraviolet. Beyond red, infrared. Several octaves are made visible by multispectral scanning. Sometimes in this film you hear sound tones corresponding to colors of specific frequencies, whether they are visible or normally invisible. For this low-frequency light, a low-frequency sound tone. We don't even have a name yet for this low-frequency color because it has never before been seen in this fashion. Contrast the same place in an ultra-high-frequency image, another invisible color. Look at several different colors at the same time, and sometimes in combination with photographs, which are usually limited to the narrow band of visible light. In the broad spectrum of visible and invisible colors, you can learn more from visible displays of multispectral imagery. Let's see how. You see your world of visible colors, as in this color television test pattern, by seeing combinations of certain basic colors. All these colors are made with just red, green, and blue. But when you sense a color, your eye cannot tell the bands that make up that color. When light of about 500 nanometers mixes with light of about 700 nanometers, you see an average, a light of about 600 nanometers, and you call it yellow. In a color mixture, the eye does not separate individual frequencies. In sound, your hearing does, something like multispectral sensing. We'll demonstrate using a Moog synthesizer, which makes music electronically. Like a tuning fork, the Moog generates pure tones of single frequencies. Here's a fundamental sound, frequency 500 hertz. Here is 700 hertz. Now, both at once. Do you hear them as an average? No. You can separate different sounds in a mixture. And so you can recognize a clarinet by its sound mixture, a pattern of frequencies. A flute has a different combination of the same frequencies. Its spectral pattern helps you to recognize it. An oboe has still a different combination of the same frequencies. Your hearing can recognize the differences. You are doing pattern recognition, something we can program a computer to do with the separately sensed colors in mixtures of light coming from objects on Earth. Using different combinations of multispectral images, we can learn to discriminate among the millions of different spectral patterns, each one caused by some object on the Earth radiating in a characteristic way. How are these technologies used to see the whole Earth, to manage Earth resources? First, we need a scanner. This one is a large aircraft scanner set up for ground test. Scanners can sense light far beyond the human eye and far beyond any lens or film. It's called a scanner because a rotating mirror scans the light from the Earth and sweeps it into a complex optical system. Here the light is split up in many different visible and invisible colors and is detected by sensitive instruments. Other kinds of multispectral scanners are mounted in unmanned spacecraft. Through solar panels, these spacecraft draw energy from the sun. They observe the Earth from orbit for periods of 1 year and longer.
6, 5, 4, 3, 2, 1, 0.
The satellite is launched into a polar orbit. With television-like cameras and multispectral scanners, the satellite orbits at about 900 kilometers in a sun-stabilized orbit. The Earth turns under it, so the systems can see the Earth in paths, the whole Earth every 18 days. Looking at the same area every 18 days shows changes in the Earth, both man-made changes and natural changes. To this unmanned satellite, it's always mid-morning on the Earth. A much larger satellite, Skylab, carries people into orbit for direct work with multispectral scanners and other sensing instruments. Inside Skylab, astronauts and scientists help to focus multispectral instruments on places of specific interest. It's a big Earth, and we want to be able to concentrate on areas of greatest value to the people on Earth. As a complement to the manned and unmanned recorders and instruments in orbit, other instruments, like this thermal mapper, are carried in aircraft, small and large. Instruments in aircraft observe in finer detail than satellites, but over much smaller areas. These flights combine the human factor, color film, radar, and other observations, along with multispectral scanning. Images are recorded electronically in such detail that the information on this one tape could overwhelm all the photo interpreters in the world if this tape had to be interpreted manually. Ground stations combine the computer's ability to handle large amounts of data with the investigative talent of people. Some tapes are read directly. Other tapes, recorded in orbit, are received at NASA stations by telemetry radio. These systems make images of the Earth you could never otherwise see. This must be done quickly, for some parts of the Earth change rapidly, as when snow and ice melt. Speed is also important, so data from orbit can be compared with ground truth. Instruments similar to those in spacecraft and aircraft measure light from known objects for recognition of the same object elsewhere. What does it mean to have such multispectral capabilities, using computers, spacecraft, aircraft with remote sensing instruments? What kinds of whole Earth problems can be solved with visible and invisible colors? Researchers and scientists carry on investigations in many fields. One problem we've mentioned, the loss of up to 1/5 of our crops every year due to infestation and disease. And in remote areas, entire forests are lost before we even realize it's happening. Here are invisible colors made visible for investigation and inventory. In this false color, the bright red patches help us to recognize healthy, growing rice crops. The blue patches are fields of burned grain stubble. Images such as these lead to more food and fibers through continuous inventories of timber, soil, and plants, and by recognition of crops. Here, for example, is a computer-processed image which has separated just one kind of crop, winter wheat. Recognizing crops by spectral patterns in such images from space is a step toward inventory of the world's changing food supplies. Dense vegetation shows along the streams in the bright red of healthy crops. In contrast, sick crops will show darker because they have a different temperature, something like sick people. Sick crops can be located while there is still time to treat them. In a remote area of healthy vegetation, the satellite records a forest fire, perhaps unseen by people. Multispectral sensing can see exactly where the fires are, even through clouds of smoke. It can recognize the vegetation associated with mosquitoes, so you can treat with insecticide only where it will do good. You can avoid spraying insecticides where they're not needed. Other kinds of problems come in managing water and ice. 3/4 of the Earth's surface is water, yet no country has enough water in the right places. This city on the ocean pipes in fresh water from rivers hundreds of miles away. Water is needed to irrigate agricultural fields. Water from snow-covered mountains can be useful. It can also cause floods. Continuous inventory of water and melting ice, even in remote regions, means better management of water resources. We are locating the best spots to harvest the fish and other resources of the sea. other problems face us. What are the limits of Earth's capacity to support population and industrialization? People are becoming more concerned with the impact of accelerating technology on our natural world. Can thermal pollution be measured and controlled? Look within the mixture of colors, the infrared, the visible, and the ultraviolet. You are seeing industrial plants and the temperature of their discharges into rivers and lakes. Can you detect pollution by gases, sometimes invisible? And notice this international boundary where one nation's air pollution flows invisibly across the border into another nation. Can you measure pollution by solid waste? Recognizing acid waste, sludge, and sewage by their spectral responses is a step toward improving our environment. Geography problems include knowing how the Earth is changing due to natural causes and due to man-made causes. In this area of several states of dense population, you see much healthy vegetation. You can analyze changing land use, study urban areas, and control their development. Where are the world's mineral and land resources? What are the potential disasters, such as earthquakes and volcanoes? How can we manage our lands wisely? Multispectral images help to predict volcanic activities, also to locate and identify minerals. They locate faults in the earth that could lead to further earthquakes. You can reduce the impact of natural disasters on people and property in the United States and in other lands. Thousands of multispectral images and other data from spacecraft and aircraft. Images of your town and your land flowing to Earth for use by federal, state, and local governments. In agriculture and forestry, in oceanography and hydrology, in geology and mining, in geography and environmental sciences. Truly, Earth Resources is a whole Earth program involving many countries as well as groups of the United Nations. Information from space shared freely by the United States as requested by other nations to fit their part of the Earth. Information about weather and about Earth resources is transmitted electronically and distributed so that people in other lands can interpret the resources of their country. With multispectral systems, we are beginning the first steps to take a continuous running inventory of the whole Earth, to increase food supplies by reducing losses due to blight and disease, and to help in cleaning the air we breathe, to help solve many problems on our precious Earth. We do not know yet all we will learn about Earth resources with these new instruments. Like Galileo's telescope, these systems will lead us to new discoveries which are not predictable. Systems for seeing many bands of visible and invisible colors, for seeing single frequency colors, and for recognizing spectral patterns found in the color coming from the whole Earth. Perhaps now you can see what you must do to the whole Earth, so your children's children will be able to tell it.